Process failure mode and effect analysis. Unlike DFMEA, which focuses on design, PFMEA focuses on processes. PFMEA should be conducted during product quality planning and before beginning production. It is a disciplined review and analysis of a new or revised process, and is conducted to anticipate, resolve, or monitor potential process problems for a new or revised product program. The PFMEA can be used in many different scenarios. Before control plans are developed for a new or modified process. When a new process, method, requirements, or technology is introduced. When an existing process is slated for improvements. During the execution of the process, for quality control measures. As we have already seen, there is a lot of back and forth information between PFMEA and DFMEA. This exchange is crucial in refining the removal of risks in a project to improve the design and process quality. Some risks will not be seen during a DFMEA, but these can appear while preparing the PFMEA. Please note, the construction of PFMEA is similar to DFMEA, which means the structure of the format is the same. DFMEA is used for design risk analysis when a new product is designed or developed. PFMEA is used for risk analysis in a process by analyzing the risk at each step of the particular process. DFMEA primarily focuses on how a product can fail to serve its purpose. PFMEA primarily focuses on how a process could fail to produce the desired output, and it is done at the process level. And we have already learned how to construct or prepare a DFMEA in the previous chapter at the conceptual level. Hence now, we will take one real example of valve PFMEA and explain one critical process fully, so that it will be easier to understand at the conceptual level as well as a practical level. Let us look at PFMEA example and explanation. Assume that engine valve component is undertaken for finish centerless grinding PFD process. Let us look at each step one by one. Process function. It is nothing but the process name. Here it is finish centerless grinding. The purpose of this operation is to grind the valve stem to the required diameter without any score marks, without any visual defects after grinding. Surface roughness should be achieved as per customer requirement, as per drawing. Hence, the requirement is to grind the stem diameter as per specification to ensure free entry of valve of stem guide. In the finish centerless grinding process, the following potential failure modes can happen. Stem dia high, stem dia low, high cylindricity, stem finish not as per specification. Visual defects. Potential failure modes: defects that can happen on product during the operation or after unloading the component has to be captured. Need to involve machine operator, production supervisor, and quality supervisor in this exercise. All the failure modes, right from component loading to unloading, have to considered. The effect of the failure mode on the product performance has to be mentioned in this column. Taking stem dia high as failure mode. If the stem dia is high, the effect will be seizing of the valve inside the engine guide bush, and the entire engine seize, and leading to valve breakage. The severity column in the PFMEA worksheet looks at the criticality of the effects of each failure mode. It reflects how bad the situation may become if the failure mode is not resolved. The severity column assigns a scale of 1 to 10 to measure just how serious the result would be. Again, this is a relative scaling based on the experience and knowledge of the CFT and MFG team. We already mentioned how each number is classified in DFMEA chapter. In this case, the effect of valve breakage was ranked as severity 5 by the CFT. It is classified as C, means critical. This column is used to classify any special characteristics, example, critical or significant, for components, subsystems, or systems that may require additional process controls. Example: C, severity rating 9 or 10. S, severity rating 5 to 8, occurrence 3. The causes have to be derived from the effect, similar to cause and effect analysis. Now, the various causes that are contributing to the effect of stem dia high are. Let us see the major ones. 1. Play and control wheel of centerless grinding machine. 2. Wrong gauge setting. 3. Dressing time high/low. 4. Less dwell time during grinding. How frequently will the cause or mechanisms that lead to failure modes occur on a scale of 1 to 10? If the likelihood is very high, then you choose rank 10, if highly unlikely, then rank 1 is best. In this case of play and control wheel of centerless grinding machine is prevented by the preventive schedule of the machine, and it is followed strictly. Hence, the occurrence ranking was given as 1 on 1 to 10 scale. The prevention control strategy used by a CFT team may benefit the process by lowering occurrence or probability. The stronger the prevention, the more evidence the potential cause can be eliminated by process design. The use of verified process standards, proven technology, with similar product or processes, programmable logic controllers, PLC, simulation technology, and SOPs, are typical prevention controls. How frequently will the cause or mechanisms that lead to failure modes occur on a scale of 1 to 10? If the likelihood is very high, then you choose rank 10, if highly unlikely, then rank 1 is best. In the case of play and control wheel of centerless grinding machine is prevented by the preventive schedule of the machine. Maybe, during a particular process, it's not possible to prevent a failure. If this is not a critical failure, then measures should be in place to detect it. By recognizing it, you also open the possibility of using prevention controls if needed. In this case, the detection method is stem diameter dimension will be measured at frequent intervals. The specified frequency is 1 component per every 100 components. It means 1 per 100 numbers, and it will be recorded in process monitoring chart or control chart. If any abnormality in the stem dia, it will be observed by the operator, and accordingly process correction will be done. Considering the manual checking, the detection rank was given as 4. The risk priority number, RPN, is the product of the 3 previously selected rankings. RPN equals severity, occurrence, detection. RPN score for this process step is 5 into 1 into 4 equals 20. In this company, an action will be taken when the RPN score crosses 80+. The recommended actions column is the location within the process FMEA that all potential improvements are placed. Example: eliminate failure modes with a severity 9 or 10. Lower occurrence on causes by error proofing. Reducing variation or mistake proofing. Lower detection on specific test improvements. With the above recommended corrective actions defined, the next step is to have a plan of action. We want to remove weak links in our processes, and we need to look at both our design and our process flow chart. We should ask and ensure the following, and fill up the format wherever applicable. Who will be responsible for putting the corrective actions in place? When can we expect these changes to be made? How will these changes affect the available resources we have for other processes and design changes? What are the highest priorities? In this case, the RPN score was 40, hence this step is not applicable. After the changes have been implemented, we can recalculate RPN to see if we were able to reduce it. The new, re-ranked, RPN should be compared with the original RPN. A reduction in this value is desirable. The residual risk may still be too high after actions have been taken. If this is the case, a new action line would be developed. This is repeated until an acceptable residual risk has been obtained.